All right, so section 2.3 is the point where we are able to use some of the things that we've sort of been developing along the way, and we'll think back on this. If you actually keep out your section 2.2 notes where we were looking at some graphs in there, it'll be helpful to think about that. I'll redraw some of them as we go. But 2.3 is going to help us to be able to do derivatives more simply. In particular, we're going to be able to do derivatives without using limits every single time. The limits are in play in the background. We're just not going to see them as we're working. Okay? So let's take a look at these. We have 4 basic rules in this section. We'll have more rules in the other sections for derivatives. The first one is called the constant rule. So, thinking about your graph, when you had a place on the graph, it was the very last example we did in the last section where it was a constant, like that. Do you remember that little section where it had that flatness to it? What happened to the graph when we took its derivative? Just that little piece. It was 0, because what's the slope along that line? 0. So the constant rule says that if you have a constant, that means just any number here, and you take its derivative is 0. That's it. Anytime you have a number, its derivative is 0. Number alone by itself. All right, now if you take a look back again into section 2.2, there was a point when we had a graph that looked like this, and we took its derivative, and I believe it looked like that. And then there was a graph that we had that looked like this, and we took its derivative, and I said one of the ways to do that is to say it looks like this. And then we had a graph that looks like this, and we took its derivative, and it became that. There's 3 of them in succession last time, right? Well, take a look. This is a cubic graph, which means it has a power of 3. And this is a quadratic, which means it has a power of 2. Here's my quadratic again, power 2. And this is a line. What does a line have a power of? Technically a power of 1. And then when we have this kind of a line with a power of 1 and we take its derivative, it actually has a power of 0. So the powers decrease as we take derivatives. That's the power rule. Now, we didn't have the details of exactly with those pictures to be able to say exactly how it decreased, but I can tell you that now. What happens is you get the exponent as a coefficient, and then your exponent becomes 1 less. So for instance, if you really had x cubed, the cube would come down to the front as a 3, and then it would turn into x squared, so you'd get 3x squared. That's the power rule. For some reason, the power rule is the one that everyone remembers. I think that's probably the only thing my husband remembers from calculus when he took it seriously, nothing else. It's been a long time, but anyway, this is the one that people seem to gravitate toward remembering. The last 2 are so common and exactly what you want them to do that you'll use them and you don't even realize you used them. Okay? This one says that if you have a constant times a function, okay, so that means a constant times x squared, a constant times sine of x, a constant times a square root, that constant that's multiplied is simply part of the next derivative. And we take the derivative of whatever the other function is and multiply that by the constant. You will use this and you won't even think you're doing anything, but you're using this rule as you're doing it. So I'll try and draw your attention to it when you do it a couple of times just so you're aware of it. And then the last one, again, you're going to use this and not really even realize that you used this. This one is the sum or the difference of 2 functions. What would you just hope and pray that this would be when you take its derivative? What would be the very best thing possible?
The constant.
No. No. Well, you guys are trying to make it too easy. No, no, no. All right. Let me move. I did say the very best. You're right. It would be really nice if, in fact, it was true that we could just take the individual derivatives of those 2 pieces and add or subtract them together. And nothing else going on. We just kind of treat them as 2 separate things, and then we just put them back together when we're done. You do your thing, I do my thing, and we'll come back together and see what we had when we finished our things that we did. And it's actually a true statement. Now, I bring this up, and I mention this in this way because this is not a true statement when we get to products and quotients. When you have multiplication and division, you can't just do that. It won't work. But for addition and subtraction, it works beautifully. Okay, so let's do some examples of how this works, and you will very quickly appreciate the fact that you do not have You do not see limit written everywhere. That's what you're going to appreciate. All right, so the first one, x to the 7th, is flat out a power rule, right? So what am I supposed to do when I have a power?
Bring your little, like, 7 down, and
Okay.
then it'll be x, and then 7 minus 1.
Which is 6, right. So is everybody good with y equals, so far, 7x to the 6th? All good? Okay. Now, 3x looks a little bit funny, and so I'll think about it with you from two different perspectives. The first perspective I want you to think about is, if I just had y equals 3x, it would be a line, right? A line with a slope of 3. And that's all derivatives are, is slope. So this derivative is just 3. Because really it's just asking what's the slope of the graph, and this is a line, and so the slope's 3. The other thing you can do, if that bothers you a little bit or you don't want to think about it that way, is you can treat it like a power rule. You can take the 1 as the exponent and bring 1 down times the 3 in front. 1 times 3 would be 3. And then you can decrease the exponent by 1. So what is the exponent going to be? 0. And what does a 0 exponent give you? 1. So this is just 3 times 1, or 3. Now, that's more work. I mean, to actually go through that every time. You're not going to, even if you start out going through that a couple of times, you're pretty quickly going to remember it each time. But that is the truth of how it works. It is compatible with the, with the rule that we have about about powers. Okay. Now, I'll make a couple of mentions as we did this. Oops. Hang on. We used rule number 4 already. Rule number 4 is about the sums and differences, right? It says that when we have a sum or a difference, we can just take the individual derivatives. We did that. So that's exactly what we did. We took the individual derivative of the first one, we put a plus sign, and we took the individual derivative of the second one. Okay. Now, this piece right here does not quite look like it fits in with this discussion, because it doesn't look like the other pieces. It doesn't really look like the rules. Is there a way that I could rewrite this so that it would look like the rules that I've been given so far?
4 x to the 1 half.
Close. Negative 1. There is something that comes about with 1/2. Do you remember what it is? Square root. So if we were given the square root of x, that would be x to the power 1/2. Good thing to think of. I think we're going to do one later on, but if not, we've established it now anyway. All right, so the part that's in the box is actually negative 4x to the negative 1. That actually looks like a power rule, doesn't it? So what am I going to do?
Bring your negative 1 down.
All right, so we're going to have the negative 4 times the negative 1, which is positive 4 now, right? And then, Emily, you told me what I'm going to have next? X to the negative 2. Remember, we are subtracting exponents, so we have the negative 1, and then we have minus another 1. All right, so now on this one, since the problem started out with an x in the denominator, no negative exponents, the problem needs to end that way as well. So the last step we'll do is we will rewrite this like so. Okay? So as a general rule of thumb, if the problem starts out a certain way, the problem should end in that same fashion. If it starts out with a denominator, it's going to end with the denominator notation. If it had started out with negative exponents, then leave it in negative exponents. There's no reason to do that differently. Okay? One other thing that I wanted to make mention of, and I'm sure that none of you are really aware of it as you did it, this problem part of it right here, we used rule number 3, the constant multiplier rule. Really, what we should have been taking the derivative of was just this. Well, that's negative x to the negative 2. But even as we did it, we multiplied the negative that was in front of the x times the negative 4. The negative 4 didn't go anywhere, right? It's still a part of the answer. That's the constant multiplier rule. Okay, let's try another one. How does this look differently than the last problem? There's some multiplication there, right? Now, in the rules that I gave you, did I talk anything about multiplication? No, and we will later, but we didn't talk about it yet. So, what's the only thing we can do in this case? What was that? Multiply it out, right. So we're going to distribute, we're going to FOIL it out, we're going to multiply it out, whatever language you're comfortable with. So, piece by piece, what do I get? Somebody tell me.
3x cubed minus 4x.
Floor is yours, Tristan. What's next?
Plus 3x squared minus
Excellent. Thank you. All right, and then yeah, on this one, nothing can combine. So we actually are good at that point, right? Now, be careful. Don't think you've actually done anything in the directions of the problem. We haven't taken a derivative yet, in other words, right? We're not to that step yet. That was just algebra. Okay, so now we're ready to take a derivative. So somebody tell me, what is the derivative of 3x cubed? 9x to the 7th. Okay, somebody else tell me, what's the derivative of negative 4x? Oh, I wrote the wrong number. I'm sorry. I said it and wrote it wrong. Thank you. Sorry. All right, somebody else tell me, what's the derivative of negative 4x? Negative 4. Okay, someone who hasn't given me an answer yet today, tell me, what's the derivative of 3x squared? 6x. I did get some voices I haven't heard today. That's good. And what's the derivative of the minus 4? That's 0. Okay? So either write nothing or write down the 0 there. That's fine as well. And again, since nothing combines, you're done. If you look at the back of the book, I'm going to guess they probably put this in descending order of exponent, but that is unnecessary. It's fine as it is as well. Any questions on that one? All right, a different notation than you've seen. Any speculation of what that might be? It kind of looks at derivative like the derivative notation from the last section, right? Like the dy over the dx or df or dx. But what's weird about it? Yeah, there's 2's in there, and that 2 in there actually means something. And you're exactly right. It means to take a second derivative. So what is a second derivative? Well, just the derivative of the derivative. Okay, so you just do the process a second time. Notationally, if you have the prime notation, we represent this as f double prime. Okay, and if you did a third derivative, what do you think would happen? You'd be a triple prime, and so forth. Okay? Just so you know, if you really wanted to do like a fifth derivative or something, we don't write 5 little primes. We actually just put the parenthesis and put the number 5 up there. So there is a point when we don't put the primes anymore, but we don't usually get that far when we're working with these problems. Okay, but in order to find the second derivative, first I have to find the first derivative. So I'm going to find the first derivative, and I'm going to use that prime notation, but you can use the other notation if you'd like. What is the derivative of x to the 6th? 6x to the 5th. Now here is a very good piece of information that we encountered a little bit a couple of times ago, right, Matt?
Yeah.
Yeah, but it doesn't say square root, it says fifth root. So do you remember how the fifth root notation is written?
1 over 5.
Yeah, so this would be x to the 1 over 5. Okay, good, good, good. All right, so if we've got that x to the 1 over 5 part, what's the derivative of that? 1/5 x to the, then you guys faded.
Negative 4 over 5.
Negative 4 over 5. That is correct. At this point, you should be able to work with fractions without too much trouble. I hope that's a true statement for you. All right, second derivative. And if we were stopping here, let me make notice. If we were stopping here, we would not leave the answer written that way. We wouldn't use the fractional exponent, and we wouldn't have it negative because the original problem did not start out that way. But we're not done with the problem yet. We're supposed to be finding the second derivative. So we're going to go one step further. So what is the derivative of 6x to the 5th? 30x to the 4th. Good. What about the 1/5 x to the negative 4/5? Negative 4 over 25. X to what power? Negative 9/5. Very good. So in terms of what the answer is going to be written like next, we are going to introduce that radical notation back in, and we are going to make the exponents be positive. So what does that mean? Well, it means that we're going to put a fifth root. It's going to be in the denominator because it was negative of the x, and you can either write x to the 9 and put the 9 with the x underneath, or you can put the 9 outside the radical. It's the same notation, just looks different. It means the same thing. So this is how the answer would be written as your final answer. Did we get all the details okay? Are you okay, Christian?
Should be there minus 9.
This right here, this negative you mean?
Yeah.
That negative is not negative anymore down here because it's on the bottom of the fraction. So the exponents change signs when they move to the bottom. Yeah. Good notation though.
Can you take an x out of the...
Yeah, you could. You could simplify this further, but you don't need to. It's fine like it is. Yeah, so if you simplified it further, you'd have 25x, the fifth root of x to the fourth. Yeah. All right, let's take a look now at this one. This one is a position function, and we're asked to find velocity. Just as a reminder real quick, what does velocity mean? First derivative. Okay, so we're finding a derivative, s prime of t. So we're going to find velocity is called v of t. The notation we can also use is this is s prime of t. But taking a look at this one, this looks like there's division going on, which is not real helpful because we don't have a rule for that yet. Any thoughts about how we could rewrite this so that we could deal with it in its current, as a current equation?
1 over the square root 18 plus rationalize it.
Okay, we possibly could rationalize it, but that's not the problem. The problem isn't the irrationals. The problem is that we have a denominator, right? I've got a numerator and I've got a denominator.
And multiply by the conjugate.
That's a rationalizing issue. That's not the denominator issue. Do you have an idea, Emily?
Do you keep the negative one here?
You can, but then you're going to have to deal with it from that perspective forward still, because it still would look then like multiplication. Think with me, there's something that you guys know is true. What can you do when fractions have the same denominator? What can you do? You can add them. So what would this become?
3 over 5.
Right, you can take the 2 and the 1 in the numerator together and put them over 5. And then, of course, you can combine the 2 and the 1. Let's think about this, but from the other direction. If I had 2 plus 1 over 5, can I move back the other direction? Is it equivalent to do that? Absolutely. That's what we're going to do on this problem. We're going to take each piece of the numerator and write it over the denominator. And we're going to do that along with the fact that, like some of you were saying, this is 2 to the 1/2 in the denominator. So why is this helpful? Well, what can you do now? You can simplify the exponents, right? Exponent rules. What do the exponent rules say you can do when you have the same base and something is in the numerator and something's in the denominator? You can subtract the exponents. So on the first one, the 4 is going to remain, and I'm going to take t squared over t to the 1/2, and I subtract the exponents. I do 2 minus 1/2. What is 2 minus 1/2? 1.5, or we're going to write it as 3/2 as a fractional form. If you write it as 1.5, it's not going to hurt anything. That'd be okay too. What about the next one? This is t to the 1. So now I have t to the 1 over t to the 1/2. What's that going to be? T to the 1/2. And then we have the last one, which doesn't have anything to reduce. So we're going to do what, I think Emily was the one who said bring it up, and then maybe somebody else as well. We're going to bring that up to the numerator as a negative exponent, because that's the best we can do, basically. All right, we can take derivatives now then, because we've got them all in exponential power form, if you will. So what is the derivative of 4t to the 3/2? And we don't need to multiply it out cleanly, just what would it be? What would I do?
6 to the 1.
Right, so I'm going to multiply the 4 times the 3/2, right? And then it would be t to the what power? 1/2, because 3/2 minus 1 would be 1/2. What about the t to the 1/2?
Minus
1/2 t to the minus 1/2, yep. And then the last one, you'd have the 3 times the negative 1/2. What would this be, t to what power? Minus 3/2. Excellent. Let's clean it up a little bit and then we'll stop for today. Okay, so this would actually end up giving you 4 times 3 over 2, or 6 square root t, right? Minus, and then I've got 1/2, so this is 1 over, and it's negative 1/2, so that's square root t. Is that good? Then minus, I've got a 3/2, so it's 3 over 2. This is t to the 3/2, so you can either write the square root of t cubed, or you could do like what you just were talking about, I think Tristan was talking about in the last problem, where you could write this as t square root t, where I have the blue circle there. We're not going to worry too much about sort of mushing them back together. That'll be sufficient. Yes?
1/2 t squared, why isn't it 1 over 2t?
Because I left it off.
Okay.
Thank you.
I was thinking.
It should be. Thank you. All right, any questions on that one?